Hey everyone, welcome to Chemistry 1112, University of Winnipeg. Dr. Carroll here. We're looking at Chapter 16, Buffers. I'm going to start with a bit of a review just to get things organized here, which is 16.1.3. And so let's just go ahead and do this question about buffers. Some information that I'll need. Let me get my right pen here. The Ka for NH4 plus. Oh, I thought I had that put in there. Okay, enter. Good. Now I'm in Paint here, so I want to go to my Paint tools. I want to get pencil. There we go. And so my Ka, I'm not sure why we still have this border around there. There you go. Ka of NH4 plus is 5.6 by 10 to minus 10. Now you might not be given that. You might get the Kb of ammonia, which is 1.8 by 10 to the minus 5. But again, for review, so the Ka of the conjugate acid is Kw, 1 by 10 to the minus 14, divided by Kb, 1.8 by 10 to the minus 5. And the pKa, I'm going to need that. So I'm going to take the log of 5.6 by 10 to the negative 10, which is then times negative 1, so 9.25. Okay, so that's the pKa. And I'm going to need the molar mass of NaOH, which is 40 grams per mole. So the moles of NaOH I'm going to be putting in a little later in this question is 1.7 divided by 40. I'm just trying to do some of the busy work right at the beginning there, 0.0425 moles. Okay. We have 1.5 liter buffer. Okay, that's how much we have. We have 0.2 moles of NH4Cl. So the concentration of the NH4 plus initially is the 0.2 moles divided by 1.5 liters. So 0.2 divided by 1.5 equals 0.133. And of the NH3 initial is the moles of that, 0.112. And it's in 1.5 liters. So 0.112 divided by 1.5 is 0.0747 molar. Okay, so what is the pH of the buffer solution? Okay, so before we add anything, I'm going to use the Henderson-Hasselbalch equation. pH equals pKa. So that's 9.25 plus the log of the base over the conjugate acid. The base is my NH3, 0.0747 over 0.113. So this becomes 9.25, and now let's get this term here. 0.0747 divided by 0.113, get a value, 0.66, and now I'm going to take the log of that value, and I get minus 0.18. So plus negative 0.18. So I can do that in my head, 9.07. I guess I should look at the answer key here. 16.1.3. Answer key is, oh, the dog just stole a bone from the kitchen. That's great. Go away, doggies. Okay, just kidding. I don't care. Section exercise 16.1.3. 9. Oh no, that's just a section exercise. Part A, 9.00. I got 9.07. Let's look at this again. 9, really? Okay, so pH equals pKa. Let's make sure we're good at that first part. So Kw 1 by 10 to the negative 14 divided by 1.8 by 10 to the negative 5 at 5.56 by 10 to the minus 10. I'm going to take the log of that answer. I get 9.25. Good. Okay, so that's good. So pH equals pKa plus the log of the base, so 0.112 divided by 1.5, and then 0.2 divided by 1.5. You know, I can really just do it like that, right? I can take the moles, so 0.112 divided by 0.2, get a value, 0.56. Take the log of that, and I get minus 0.25, and then add that plus 9.25, and I get 8.99, it rounds to 9.0. Okay, so it's 9.00. So did I make a mistake in getting the concentrations? Let's see. My NH4 plus would be 0.2 divided by 1.5, which is 0.133, and my NH3 is 0.112 divided by 1.5, which is 0.0747. Okay, so that's good. Divided by 0.113, and then I take the log of the answer, and I get minus 0.18. So what is happening, or why am I getting two different numbers? 0.112 divided by 1.5. Okay, start again. Base 0.112 divided by 1.5, and all that divided by 0.2 divided by 1.5. 0.56. Okay, and then take the log of that. So I was just pressing the buttons wrong. Okay, so you get 9.00. It's better not to divide by the 1.5 and use the moles, because you're also introducing a bit of round off error. And if you can avoid that by doing the moles over the moles, it helps. Okay, so that was part A. Took me a bit longer than I wanted to do that, but you know what? It was good because you saw some of the trials and tribulations that can happen. If you didn't want to see all that, just watch this in 2x speed, where I'll sound like Alvin and the Chipmunks. Part B. What would be the pH after adding 1.7 grams of NaOH to the buffer described in Part A? So let's get the moles of NaOH. We already did 0.0925. 1.7 over 40. 1.7 divided by 40 is 0.0425. That became messy, didn't it? Let's see. 1.7 over 40. 1.7 divided by 40. 0.0425. Okay, so now we think of the hockey goalie. Incoming strong base. Who's going to make the save? The acid component, the NH4 plus. And then we're going to get NH3 plus H2O. So the initial number of moles of OH minus that comes in is 0.0425. That's a 4. The NH4 plus that we started with in terms of moles is 0.2. Well, they're going to use 3 decimals, fine. And my NH3 at the beginning is not 0, it's 0.112. Okay, so we have moles of each of these. Then the change in the number of moles, well, OH minus better be my limiting reactant. If it's not going to be a buffer. We are going to, if it wasn't the limiting reactant, then we would have lost our buffer capacity, something we're going to talk about more details later on in this lecture. So we lose 0.0425 of the OH minus. We lose 0.0425 of the NH4 plus, and we gain 0.0425 of the NH3. So at equilibrium, we're going to have no OH minus. We're going to have 0.2 minus 0.0425, 0.1575, and then 0.112 plus 0.0425 is 0.1545. Okay, so now I can get the concentrations, but like I said, I just want to get the pH, so I can just go use the mole ratio, which will work fine. In fact, the volumes of the buffer is not going to change much. Sodium hydroxide is a solid. You put these solid white pellets, so you dissolve them into the solution. The 1.5 liters is not going to change significantly from 1.5 liters. The pH is the pKa, 9.25, plus the log of the base, 0.1545, over 0.1575. Okay, so you got 0.1545, 0.1545 divided by 0.1575. Okay, then I'm going to take the log of that answer, and I'm going to add that to 9.25, and I get 9.24. Really? That it just goes down by that small amount? Let's see, 16.1.3. Yep, 9.24. So you see how important it was to deal with that. And it goes down by a small amount from pKa. Now, in terms of from the neutral buffer pH was 9.0. Neutral buffer. Why did I say neutral buffer? The buffer has prepared, before we add in any sodium hydroxide, has a pH of 9.00. Then we put in some base, okay, 1.7 grams, that's not insignificant, and the pH goes up, as you'd expect, because we're putting in some base. But it doesn't go up drastically high. That's what would happen if we didn't have a buffer. But we do have a buffer, so the ammonium cation portion of the buffer, the weak acid portion of the buffer, absorbs the incoming strong base. And in so doing, that sacrifice, we still do get more ammonia formed, so we do get the pH going up, so it goes to 9.24. Okay, and part C, once you just make the comparison, I mean, I could expand upon this, but the question didn't ask on it, and say, what instead if we put in some hydrochloric acid? Well, then the NH3 would be the one making the sacrifice. If we add 1.7 grams of NaOH to 1.5 liters of water, so here we're saying, what if we don't have any buffer and we just take 1.7 grams, which is 0.0425 moles, and mix that in 1.5 liters. So 0.0425 divided by 1.5 is 0.0283 moles per liter. And now I can get the POH, 1.54. So the pH is 14 minus 1.55, sorry, 14 minus 1.55 14 minus 1.55, and I get 12.45, which is a lot more than 9.24. Okay, again showing the point of the buffer. Okay, so I'm glad we did that, and let's now go to our new topic, which is still related to this topic. So I want to go to here, capacity and preparing the buffers. Okay, so buffer capacity is the amount of added H3O plus or OH minus that the buffer can tolerate without exceeding its specified pH range. If enough H3O plus is added, the buffer is destroyed, right? And you want to keep in that 1 to 10 or 10 to 1 ratio within that sweet spot. So the buffers depend on how much you have, right? Because as time goes by, you're going to get less of it, and the volume of the buffer solution. And we'll see some calculations of those. Buffer solution of overall concentration 0.5, so if you get the total concentration of 0.5, that's 5 times the capacity of one with an overall concentration of 0.1. 2 liters of 0.1 molar buffer have twice the capacity of 1 liter. Okay, so, oh yeah, I remember there's some tricky stuff with this, but we'll get through it. So, let's try example 16.6. Biochemists and molecular biologists use phosphate buffers to match physiological conditions. Buffer solution that contains, what is that? Sodium dihydrogen phosphate, so just the anion we look at, right? We don't care about the sodium, is the weak acid, and HPO, what do they call that one? H2PO4 minus, and HPO4 minus is the weak base, right? It's the conjugate base of H2PO4 minus. The pH is close to 7, okay? Biochemist prepares 0.25 liters of a buffer solution that contains these concentrations: 0.225 molar HPO4 minus, 0.330 molar H2PO4 minus. What's the pH? And then we're going to add some stuff in. So H2PO4 minus acts as the acid. So that's the equation you start with. And your K EQ would be the second ionization of H3PO4. Fine, okay. So pH equals pKa plus the log of A minus over that. Now, you can look back in the tables to get the phosphoric acid, Ka2, get the pKa of that, turns out to be 7.21. Look at that yourself, plus the log of the base 0.225 over 0.33. So the pH is close to 7, 7.04. So that's the way you've prepared that buffer. Now you want to see if it can do the job. So when we bring in the OH minus, we put 0.4 grams, so that's 0.01 moles. Okay, so the moles initial, I'm going to put it above here. It's 0.01. Was that how much OH minus we had to put in? Is the buffering action destroyed by 0.4 grams? So 0.4 over 40 is 0.01 moles of OH minus. The H2PO4 minus present is its concentration times the volume, 0.0825. Okay, so we got lots. Amount of base added is considerably less than the amount of acid initially present, so the solution will still act as a buffer. The added base raises the pH, however. Yeah, it does, because reaction with the OH minus with the buffer increases the amount of HPO4 minus. Okay, and we leave it to you, so I'll leave it to you to use the procedure to show the pH after the addition of this solid is 7.17. So even the book's getting tired of doing this. Now, addition of 5.25 grams would exceed the capacity. Okay, so that, let's actually do that one. Let's do the practice exercise. So 5.25 over 40. 5.25 divided by 40 is 0.131 moles. So your OH minus plus your H2PO4 minus goes to form your H2O plus HPO4 2 minus. So the OH minus I put in is 0.131. The H2PO4 minus I started with is 0.0825. And I know I have some of the other stuff starting with 2, but that's not really what I care about. Oh no, I do care about that. It wants me to get the pH of the solution. Okay, so the HPO4 2 minus I start with is 0.2 HPO4 2 minus I start with is 0.225. I just shut off my calculator. There it is. 0.225 times 0.25. 0.225 times 0.25 is 0.05625. Okay, so now, so that's the initial number of moles. My change in moles, well, you see here that we've destroyed the buffer because I put in more hydroxide than the H2PO4 minus had. So I lose all the H2PO4 minus. I lose the same amount of the OH minus, and I gain 0.0825 of the HPO4 2 minus. So my final, my hydroxide is going to be 0.131. This is the moles, 0.131 minus 0.0825 is 0.0485. And I have 0 of the H2PO4 minus. That became the limiting reactant. And the HPO4 2 minus is 0.05625 plus 0.0825, 0.139. Fine, I'm rounding now. 0.13875. Good, you happy? Okay. And so my final concentrations, this is all happening in a 0.25 liters. So my OH minus is 0.0485 divided by 0.25, which is 0.194. And my HPO4 2 minus is 0.13875 divided by 0.25, which is 0.555. Okay, so let's see, practice exercise 16.6, and OH minus is 0.049 molar. No, that's a mistake. They meant to say that is the so let's describe an example 16.4. 16.4. Oh, I did a whole different question here, didn't I? I'm doing the information from 16.6. I'm doing 16.6. Okay, so anyways, I have this hydroxide in excess. Now, I can still do something with this. The pH is going to be dictated by the OH minus, way more than the HPO42 minus, because OH minus is a strong base. HPO42 minus can accept a proton from H2O to form H2PO4 minus and some hydroxide, but that amount is so much smaller than the amount of hydroxide just present here that it can be ignored. So and that's an important point about excess mixes, that it's the strong base that wins out, and we'll get to titrations, we'll see that as well. So I'm salvaging something out of this. Log of 0.194 and then 0.71, so 12.3. Let's try it again. Log of 0.194 is 0.71. 14 minus 0.71, or that's POH is 0.71, so 13.3. Okay, so you can try the real practice exercise 16.6 on your own, where you're looking at the solution in example 16.4. Okay, so buffer prep, we've mentioned it, we've done examples. I already said that the pH range should be within pKa plus or minus 1. Best capacity is when the target pH and the pKa of the acid you choose in the buffer are as close to each other as possible. Okay, so if you wanted to, let's say you're looking at some biological enzyme and you wanted the pH range to be 6 and 8, you might choose the H2PO4 minus HPO42 minus buffer. Or perhaps in some kinds of beers, the enzymes work best if the pH range is between 9 and 11, you might choose the HCO3 minus CO3 2 minus buffer. Okay, so there's different possibilities that you can use. Okay, let's say you wanted to have a pH of 5 and you were using the acetic acid acetate solution, so you wanted the pH to be 5, and there's your pKa. So when preparing the buffer, it's sometimes useful to know the ratio of the conjugate base to the acid. So like I didn't know what the acetate or acetic acid were themselves, but I could do 5 minus 4.75, take the inverse log of 0.25, and get the ratio of acetate to acetic acid. So if you want to prepare a buffer with a pH of 5, sodium acetate and acetic acid should be added to the pure water in a molar ratio of 1.8, in a given volume, so 1.8 moles of the acetate for every 1 mole of the acetic acid. Okay, so let's try example 16.7. This one's a little bit wild, but let's give it a shot. We'll just try one of these. Okay, so good. We've already talked about acetic acid and the acetate. So what mass of sodium acetate and what volume should be used to prepare a 1.5 liter of buffer? So remember the pKa is 4.74. I'm going to put some of that in the margins here. Did the book round it off to 4.75? What did they do there? 4.75. Okay, fine. pKa is 4.75. Okay, so and the overall concentration is going to be 0.15 molar. Problem specifies a solution volume of 1.5 liter with a total molarity of 0.15 moles per liter. So the total molarity is the combined concentration of the two buffer components. By the way, this is the only book I've ever seen where they've tried this kind of question. But this book does break the rules on all sorts of things. But that's what makes it so cool, right? Okay, where's my royalty? Where's my endorsement fees for saying that? the acetate is going to be some concentration. The acetic acid is going to be some concentration. Those are the two parts. Together, the total molarity is 0.15. Okay, how many moles do we have in the system? The system together is 1.5 liters, and the overall concentration is 0.15 moles per liter. So 0.15 moles per liter times 1.5 liters, the liters cancel, of course, and you get 0.225 moles. So the moles of the acetate ion plus the moles of acetic acid together have to give us 0.225. Okay, so I'm just setting things up here. The ratio has to be 1.8. We got that from our discussion above, example 16.7, the ratio of the acetate moles to the acetic acid moles. So the acetate moles is 1.8 times the acetic acid moles. Okay, so we did that before. Now we got to just find some. We've got so many unknowns here. We got to start doing some substitutions and things. Substitute and calculate the required moles of acetic acid. So we know that the acetate is 1.8 times acetic acid, right? So that 1.8 acetic acid plus acetic acid is the total number of moles, 0.225. So add them together, you get 2.8 acetic acid is 0.225. So the moles of acetic acid is 0.225 over 2.8. So we're actually doing a substitution here. So moles of acetic acid is 0.0804, and the acetate would be 0.225 minus 0.0804. So now we know the moles of acetate and the moles of acetic acid. Now you don't just pour in acetate, you pour in sodium acetate. So sodium acetate, the mass is the moles of it, 0.145 times the molar mass of sodium acetate. So you're pouring in 12 grams of sodium acetate. Now acetic acid is used as a, when you're pouring it in, has a very concentrated liquid, 17.45 moles per liter. What is that? C equals N over V. So V equals N over C. So 8.04 by 10 to minus 2 moles, 0.084 moles over 17.45 moles per liter, and they wanted to convert it to milliliters. So to prepare the buffer, according to the conditions asked, you have to spoon in 12 grams of sodium acetate and pour in 4.6 mils of acetic acid, then top it off to 150 mils. And that's the way you make that buffer. And you can try practice 16.7 on your own. Okay. I never liked 16.8 example. I'm not going to bother with it. Okay. And you can try the section exercises on your own. Okay. So now I want to get into at least a bit of the acid-base titrations, just the general definitions, and then the titration curves I will discuss in the next lecture. So acid-base titrations, and these are on page 784. I should tell you that we just go up to 794. Do I do the rest of the chapter? No, I don't. Solubility, equilibrium. No, we don't do all that stuff, all that KSP stuff. So this chapter, there's lots that we don't do. So we just go from page 784 up to 793 inclusive. 784 to 793. No. Egg. That's K-N-O-W. Know those pages. 794 and onwards omit. Okay, so this we got to know. 784. page we're on right now. So here we go. Let's just look at what a titration is. So you have a Erlenmeyer flask. Hopefully you'll be able to do this in class in a lab. Otherwise, you'll do it in some virtual way. And so you have an an Erlenmeyer flask. That is, and you've done this in grade 12, I hope, where you're going to put in either an acid or the base. Let's say you're putting in an acid, typical one, HCl, of some unknown quantity. Okay, and a typical volume is 25 mils. So that's my sample volume. Some old people like me call it the aliquot. A sample of HCl is placed in an Erlenmeyer flask. We don't know what the concentration of the HCl is, and so we do a titration. Another use of titration is not knowing what the identity is of the chemical and using the data to get the identity. Another thing we're going to have to drip in here is an indicator, so we know when the endpoint occurs. When the endpoint occurs, the indicator changes color. It's often very close to the equivalence point, where the number of moles of base delivered to the acid in the Erlenmeyer flask equals the number of moles of acid originally present. That's called the equivalence point. So I'm just doing a bit of vocabulary here. Okay, so we have our sample, we have the indicator, we might have a probe measuring the pH per drop of incoming titrant, and that would give us our titration curves, which we're going to get into very soon. So then we have this long tube dripping in the base, and that's called a burette. This is the American way, this is the Canadian way, burette. Okay, and it's a long glass tube with lots of markings on it, so you can get a more accurate reading of the volume dispensed into the Erlenmeyer flask. Okay, so it could be any OH, and this you have to know carefully the concentration. Okay, you may have to do a whole process, very boring, but it has to be done. Standardized solution. That means very carefully measuring it against these other calibrated values, so you get a really good value of your incoming NaOH. It is called the titrant. The thing in the flask is called the titrate, but titrate also is a verb, so you say that the titrant titrates the titrate. I know it sounds silly, but that is what's happening. So this is a classic setup for a titration. I could have the base in the Erlenmeyer flask and the acid in the burette. You also have a little magnetic jelly bean spinning around to keep things nicely mixed. So let's read it here. The amount of an acid in a sample can be determined by adding a solution of base of known concentration until the amount of base added exactly matches the amount of acid. Similarly, the amount of base can be determined by adding a solution of acid of known concentration until you match that. And that procedure is called titration. The solution to be analyzed and is placed in a beaker or flask. A sample, usually a small sample. You don't put like 5 liters to be titrated. 25 mils, 10 mils are common, 50 mils sometimes. Second solution of known concentration called the titrant is added slowly by means of a calibrated measuring vessel called a burette. And they call this a Canadian book, yet they use the American spelling. Okay. Anyways, one type of titration, you have a solution of a strong base, like sodium hydroxide, is added slowly to a solution that contains an unknown amount of an acid. Each hydroxide ion added to the acid accepts 1 proton. As the titration proceeds, fewer and fewer acid molecules remain, but the solution is still acidic. At the stoichiometric point, now that is another name for equivalence point, so this book decides to use another word for equivalence point. They call it stoichiometric point. Just enough hydroxide has been added. Neutralization happens, right? You get complete neutralization of the acid in the original sample by the incoming base. The The hydroxide ions of the next drop don't react because the acid molecules are no longer present. Before stoichiometric point, you had excess acid. After, you have excess base. If you know the molarity of the titrant and measure the volume of the titrant, you can calculate the number of moles present. Here's a picture of titration of HCl by NaOH, so we don't put in the spectator ions. Part A, initially the HCl solution contains many hydronium ions. So there they are, hydronium ions. And then at the stoichiometric point, they're gone. We don't have them anymore. And then after, we have many OH minus. And you see that there's my burette, there's my stopcock or my valve. If it's perpendicular, there's no delivery. If it's parallel, you get the drippings. And a pink color, which means phenolphthalein was the indicator used. There's lots of indicators that can be used. Maybe a dozen common indicators are used in the acid-base titration world. And the endpoint is when the indicator changes color. And you want to have that endpoint within the equivalence point range. You don't want to have color changes outside of the equivalence point. That's not very helpful. So the reaction, which is really happening, is a very simple reaction. It's OH minus plus H plus goes to H2O. That is the neutralization. And we can make if it's a 1-to-1 ratio of acid to base in my overall molecular equation, I make this little shortcut that I always like to do. MAVA equals MBVB. If it's not a 1-to-1 ratio, then you can't do that, but the majority of the ones we look at will be a 1-to-1 titrations. So MA times VA, molarity of acid times volume of the acid. So the moles of acid originally present equals the moles of base added. So this is what's happening at the equivalence point. And some of these questions don't ask you to do that, but I always think you should, because then it gives you some guidelines and a clearer picture of what's happening in these processes. These pictures here are all a strong acid being titrated by a strong base. Some people write strong acid with a strong base. I don't like that notation, that wording. I think by is better. So that means the strong acid is in the Erlenmeyer flask and the strong base is in the burette. Other ones we'll see in this section is a strong base by a strong acid, a weak acid by a strong base, and a weak base by a strong acid. You never titrate with a weak acid or a weak base in the burette. It just doesn't give you useful data to help identify the unknown acid or get the concentrations of the acid. You never titrate a weak acid by a weak base or a weak base by a weak acid. So your titrant is either going to be a strong acid or a strong base. Your titrate is going to be a strong acid, strong base, weak acid, weak base. So those are the possibilities of titrations that can happen. Okay, so we have here, I don't want to look at the answer yet, I want to just try it my way. Industrial wastewater often is contaminated with strong acids, for sure. Environmental regulations require that such wastewater be neutralized before it is returned to the environment. 150 ml sample of wastewater was titrated with 0.125 molar sodium hydroxide. 38.65 mils of the base was added. So typically 2 decimals are used in burette data to reach the stoichiometric point. What was the molarity of the acid, the hydronium ions in the sample wastewater? Okay, so MA, oh, I lost my pen there. Sample 69, I'm going to go to the burette thing here. Burette, that's not a burette. I'm going to go to the paint thing here. Okay, so I'm going to exit all out of it. And now I cannot even, okay, I'm going to have to minimize here and go to paint. Okay, so I'm opening paint again, and I'm going to do the question. I'm not going to change anything here. So this is the wastewater. So I want to get the molarity of the acid. So the molarity of the acid is molarity of the base, volume of the base, over the volume of the acid. So the molarity of the base is 0.125. The volume of the base is 38.65. And I can keep it in mils because the mils will cancel out. The volume of the acid sample is, oh, this is actually a larger sample than I would ever use, but 150. Okay, so that's fine. So the molarity of the acid becomes 150 mils is a large sample size. I'm sure they had their reasons. So 0.1, maybe there's lots of junk. So lots of volume because you got lots of junk in wastewater. That's for sure. That's why it's called waste. 0.125 times 38.65 divided by 150 is 0.0322. I bet the book rounds it to 0.032. Oh no, they keep it 0.0322. Yeah, because that is 3 decimals. Okay. Let's try practice exercise 16.9. The book does it a longer, more boring way. My way's better. Acidic component of vinegar is acetic acid. 5 mils of vinegar is added to water, and the solution titrated with 0.125 molar NaOH. It took 33.8 milliliters to reach the stoichiometric point. Calculate the molarity of acetic acid and vinegar. Okay, so we'll assume that the volume of the, doesn't say how much water, but I'm going to assume that that will come out in the wash. So my molarity of the acid, it wasn't worded that well, that question is the molarity of the base, 0.125, times the volume of the base, 33.8, over the volume of the acid, and that's going to be 5. So we're going to get 0.125 times 33.8 divided by 5.845. Let's see, example 16.9. 0.845. Yeah, that's good. Okay. So now let's go back to here. How do we know if we've reached the point? An indicator is going to change color. Indicator is a molecule whose color depends on the concentration of hydronium ions. So here is a strong acid being titrated by a strong base. So you have this initial portion here, and then near the equivalence point, you go very steeply up, and then you go across. Now I really do need the pen, so I'm going to begin the titration curves in my next lecture. Okay, so we'll start on page 786 in our next lecture. Have fun!